Hello everyone, welcome back to Technologies Discussion channel. This video, I like to draw a conclusion on EMC shielding effectiveness. In this video, I'm going to discuss the effectiveness of shielding when against low frequency, which is mainly dominated by E field or H field. At high frequency, this is most of the time dominated by far field, which is the plane wave. So basically, this video, I will explain how you can actually build your shield so that it is more effective, whether at near field or far field. So basically, this will be the objective of this video. Guys, if you're keen to know more about EMC or maybe the shielding effectiveness of EMC, basically, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on all this. This is my email. If you have any question regards on this discussion, please drop me an email. Okay, or if not, I actually prefer you guys to ask me your question through the comment. Before I continue, guys, I like to urge you guys to help me by like this video. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Before we talk about the shielding effectiveness, we need to know whether it is actually considered near field or far field. What is actually near field and far field? Okay, so this can be explained in this diagram over here. So anything less than lambda over 2 pi, this is what we call near field. Anything more than lambda over 2 pi, this is what we call far field. Okay, so basically in short, when it is actually near field, it is mainly dominated by either the E field or H field. They are actually independent, as you can see from here. Okay, so the E and H field are actually independent and they actually behave differently. Okay, so basically E will have high impedance while H has low impedance. As for far field, okay, like I mentioned earlier on, this is something beyond that is lambda over 2 pi, as you can see from this diagram here. In this far field, the E and H plane, they basically will be joined together as a plane wave, while the impedance is actually fixed at 377 ohm. Why this is important? Okay, because the mechanism that we design as a shield, they actually work independently, actually depend on whether the source will be a high impedance E field, whether it is a low impedance H field or a plane wave. And so basically the design actually work differently based on the source, whether is it E field, H field, or plane wave, we actually design accordingly. Now, let's focus on the low frequency. Okay, so at low frequency, okay, so typically below 1 megahertz, okay, for many application, okay, the wavelength is long. Okay, so basically, let's take a look on this diagram. So basically, this is actually for low frequency. Under low frequency, the wavelength will be long. So imagine this will be moving further away from the source of noise, let's say. So basically, most of the time, under low frequency, the near field actually dominate. So this is what you mean. Because the wavelength being long, this you can imagine that they are actually pushing further away. So hence for low frequency, typically it will be dominated by near field. Okay, so as it explained over here. Okay, so basically at low frequency, okay, typically below 1 megahertz, okay, so the wavelength is long, so the near field extend far from the source. Okay, so this is where shielding is most challenging and field dependent. So basically, in short, okay, it is always very challenging to shield against near field. It is definitely much more easier to shield against far field. Let's discuss about the shielding against the low frequency electric field. Okay, so basically for electric field, they won't have any concern. It is much easier to build a shield. Okay, so the mechanism, if you are high impedance field, shielding work primarily through reflection. If you still remember, when we build a shield, we actually want to have reflection, absorption, and also the multiple reflection actually degrade the shielding effectiveness. So basically, when we counter against low frequency electric field, most of the time reflection will be the dominant factor. Okay, so the shield act as a conductive barrier that create an equal potential cage. Okay, so the incoming field, okay, which is the induced field, they actually induce the charge on the outside surface, and the resulting potential difference drive the image current that cancel the incident field. Okay, so basically this is how we can curb against low frequency electric field, mainly will be by reflection, and this is actually very effective. Next, okay, so this is what I mentioned just now. Okay, so basically for low frequency electric field, this will be very effective. Okay, for even a very thin conductive layer. Okay, so the keyword is the shield must be a conductive layer, such a like a pane, okay, a conductive pane foil, or even a very poorly grounded mesh. They can at least provide 80 dB of attenuation. Okay, so basically you actually successfully curb away the low frequency electric field. The key is to have a continuous conductive path. So this is also very important. Make sure that you remember to ground the shield. Okay, so without grounding the shield, it will not be that effective anymore. So keep this in mind. You need to ground the shield. This is absolutely critical to provide a path for the induced current to flow to earth, complete the cancellation mechanism. Okay, so basically in order to have reflective to be effective, okay, make sure you ground the shield. So basically when you actually provide the grounding, this actually provide a path for those induced current to flow to the earth. So one key example will be shooting a sensitivity audio cable, okay, from this 60 hertz AC hum from a power line. Okay, so a very simple, you just need to build a shield. Okay, so the well grounded at one end, this is actually very effective. Okay, so basically you have a better idea now. So basically when you actually want to curb against low frequency electric field, this is actually very easy, and most of the time you just need to have the reflection in order to curb all this low frequency electric field. Next, this is slightly more challenging when we actually want to build the shield against low frequency magnetic field. Okay, so basically this may be even no solution. Okay, let's take a look here. Okay, so the H field are low impedance field. Okay, so if you still remember, the E field is actually high impedance, but the H field are low impedance field. Hence, the shielding work primarily work through the diverting the magnetic flux. Okay, so at low frequency, okay, both the absorption and also the reflection is totally ineffective. So the only way is to divert the magnetic field, which I'm going to explain later on. Okay, so basically we have no way to reflect it, and we have some minimum so-called absorption. Okay, however, it's not effective. Okay, so the shield in fact will provide a low reluctant path, okay, for the magnetic flux lines to travel around the sensitivity area instead of through it. Okay, so later on I will have a diagram to explain all this. Okay, so when we actually want to shield against low frequency magnetic field, this is going to be very challenging because firstly the reflection is poor, okay, because the wave impedance is low. Okay, so basically this is one issue. Absorption, okay, it works somehow a little bit. However, at low frequency, absorption is not that effective, and hence we have bigger problem when we actually want to tackle the low frequency magnetic field. Okay, so basically if we want, okay, so basically the shield must have the high permeability. Okay, so material like Mu metal, magnetic alloy, or even very thick pure iron. Okay, so they have permeabilities thousands of times greater than free space. So this in fact will act as a short circuit for the magnetic flux. As I mentioned earlier on, okay, because for low frequency magnetic field, properly absorption will be the one that actually working. So hence, okay, the shield need to be very, very thick. Okay, so basically more material actually provide more cross-section area to carry the flux without saturation. We must be also very careful to avoid saturation. Okay, so if the magnetic field is too strong, okay, it will saturate the high permeability material, causing it to drop to nearly one. Okay, so this actually makes the shield completely ineffective. Okay, so therefore, this is actually the biggest challenge. Okay, so basically, I have also explained in terms of low frequency magnetic field, which is the most challenging one to shield against. Okay, so next, okay, so I'm going to discuss on the shielding at high frequency, okay, far field. Okay, so at high frequency, okay, so basically imagine this, at high frequency, the wavelength will be small And therefore, imagine this will be pushing nearer. So therefore, most of the high frequency, they will actually happen at the far field, as it mentioned over here. Okay, so the radiation is actually the plane wave. E and H, they basically couple, which means that E and H, basically they join together and has a impedance of 377 ohm. Okay, coming to the mechanism, the shielding effectiveness is mainly dominated by absorption loss. Okay, with refraction also play a key role. Okay, so basically for plane wave or far field, okay, basically will be a combination of absorption and also refraction. Let's come to the absorption loss first. Okay, so this is actually the primary mechanism. When an EM wave hit a conductivity material, it induces current, okay, which I have explained earlier on. Due to the electrical resistance of the material, this energy is converted into heat. Absorption loss actually increase with the square root of frequency, conductivity, and permeability. Okay, so this is even a very simple thin copper foil. They will be actually very fantastic against high frequency. Okay, so basically the absorption loss is very high at high frequency. So in short, okay, the absorption loss will not be that effective at low frequency. However, at high frequency, it will be very effective. Next, okay, as I mentioned earlier on, okay, beside absorption, we also have the reflection loss. Okay, so this is still very important. Okay, but they are actually less dominant at low frequency E field. Okay, so it actually depends on the mismatch between the wave impedance and the shield intrinsic impedance. Next, we also need to consider the multiple reflection. If let's say the absorption is not that ideal, then we need to consider this multiple reflection. Okay, so basically a mirror correction factor for wave reflection inside the shield. Okay, so basically if you need to know a little bit more on this absorption, reflection, and multiple reflection, please see the playlist in order to know more. Guys, I also need your help. Okay, if you have learned something from this video, please help me by like this video and subscribe to this channel. Once again, thank you so much for strong support. Let me continue. Okay, so let me quickly discuss on the shielding effectiveness against electric field and also against the magnetic field. As for electric field, okay, the total loss for an electric field is actually mainly dominated by a combination of the absorption and also the reflection loss. The multiple reflection loss correction factor B, okay, is normally neglected. Okay, so in the case of an E field, okay, since the reflection loss is so great and the correction term is small, okay, so typically for reflection, okay, it can be even like hundreds, and for the B term, they can be in term of like maybe 5, 2, etc. So basically, the reflection is so much time bigger as compared to the B. So hence the B term we can actually neglect. However, at low frequency, okay, reflection loss is the primary shielding mechanism for E field, but we can't do anything, okay, against the magnetic field. So therefore, at high frequency here, absorption loss is the primary shielding mechanism. In short, over here, you can see that when we actually work against electric field, okay, so at low frequency, the reflection will be the dominant factor. At high frequency, absorption will be the dominant factor. So basically, when we curb, okay, especially for low frequency, then we will design a reflection. When we actually curb against high frequency for electric field, then we will design a thicker shield in order to combat against the noise source of electric field. As I mentioned earlier on, this magnetic field will probably has a little bit challenge in order to curb it. Okay, so the total loss for a magnetic field is actually obtained by combining the absorption loss and the reflection loss. If the shield is thick, okay, absorption loss exceeds 10 dB, the multiple reflection B can be neglected. Else, the correction factor B must be included. Okay, so basically, later on, I will actually explain another way to curb the low frequency magnetic field. Okay, so let me draw a conclusion. Okay, because the characteristics impedance of a conductor actually increase with frequency, so therefore the reflection loss actually decrease with frequency. So from here you can see that at the low frequency, okay, it is mainly dominated by reflection. When frequency actually increase, you can see that the reflection actually decrease. So basically, this is what it means. So basically, when the frequency getting higher and higher, okay, the reflection loss actually will be decreased together with the frequency. As for the absorption loss, is actually work on the other hand. Okay, so basically when the frequency increase, you can see that the absorption loss actually increase. So basically this is for the absorption loss. Okay, so this is because okay the skin depth actually decrease with frequency. Okay, so all this I have explained earlier on my playlist. So again, please see the playlist in order to understand all this better. So basically in short, okay, under this low frequency, okay, it is mainly dominated by reflection. Okay, however, for magnetic field, you don't have any reflection also. So therefore, over here you can see that magnetic field has some issue when we want to so-called shield against low frequency. Okay, both the reflection, both the absorption is not effective. So therefore, as I mentioned earlier on, electric field and also plane wave, they are actually very effective. Okay, basically you just need to concentrate on the reflection. However, when the frequency increase, you can see that absorption increase. This is because the skin depth actually decrease with frequency. Okay, so basically, thus the characteristics shape of the shielding effectiveness with absorption loss dominate at high frequency and reflection actually loss dominate at low frequency. Okay, so basically, this is the key explanation what I mentioned about the shielding effectiveness based on frequency. Next, this is what I mentioned earlier on. This is what I want to explain clearly also. Okay, so therefore, as I mentioned earlier on, the reflection loss to a low frequency magnetic field is almost negligible, okay, because there's totally almost no reflection loss for low frequency magnetic field. And also due to multiple reflection, this effect is even more problematic, especially in a thin shield. So therefore, the primary loss for magnetic field is actually absorption loss. However, okay, both the absorption and reflection loss are actually very small at low frequency. Hence, the total shielding effectiveness is actually very low. So therefore, okay, it is always very challenging to shield low frequency magnetic field. Additional protection against low frequency magnetic field can be only achieved by providing a low reluctance magnetic shunt path to divert the field around the circuit being protected. Let me explain with a diagram. For example, this is a region. Okay, basically these are all the sensitive components that I want to actually protect. So therefore, from this diagram here, you can imagine that these are all so-called provide this low reluctance magnetic path here. So basically, the magnetic path instead of propagate straight to the sensitive area, this path actually provide a low reluctant magnetic path, and basically they will be moving away from the sensitivity region. So this is how we can curb against low frequency magnetic field. Okay, so basically all the explanation is mentioned here. The magnetic material used as a shield by providing low reluctance magnetic shunt path for the magnetic field to travel. So basically, this is the only way that we can curb against low frequency magnetic field. Next, okay, let's do a quick summary. Okay, so basically I have explained all this in deep detail. What is actually reflection, absorption, and also this multiple reflection. Okay, so how it work? Okay, so basically for reflection, it act like a mirror, and because of impedance mismatch, okay, because E field actually has a high impedance, and the conductivity, okay, which is the shield, is actually most of the time low impedance, and therefore they actually has a high impedance mismatch, and hence because of this, reflection is actually very effective against E field. Okay, so basically this is what it means. The key driver is basically the surface conductivity. Okay, so it is actually most effective for high impedance wave. Okay, so basically as for absorption, okay, the wave energy is converted to heat as current flow in the shield. Okay, remember this. Remember to ground the shielding. Okay, so basically it is actually a product of permeability, conductivity, and also frequency. Okay, so the dominate mechanism for magnetic fields and high frequency. As for the multiple reflection, okay, we are going to have this multiple internal reflection within the shield material. Okay, so this can be very small, and most of the time you can actually neglect it. Okay, so however, for low frequency magnetic field, then we need to take a little bit more concern, okay, especially if the shield is thin. My last slide, okay, so basically this is what I want to draw a conclusion. I have discussed extensively the shielding effectiveness versus the low and high frequency. So no issue when we actually need to tackle the E field. Okay, so basically we have excellent shielding, and in fact it will be very easy, one of the easiest way to shield. Okay, even for a very thin. Okay, so basically we need to have a conductive material. Okay, so basically this is actually driven by capacitive coupling. Okay, so basically for high frequency, okay, so the E field can be excellent. So basically these two are actually the same. When they are actually at far field, they become far field. Okay, so basically this is an excellent shielding. They basically will be governed by absorption loss. If you still remember, for low frequency, reflection will be effective. For high frequency, absorption will be reflective. As for magnetic field, okay, as low frequency, it is always very challenging, very difficult to shield. As I mentioned earlier on, if you need, then you need to consider this MU metal. Okay, so basically this is actually driven by inductive coupling and magnetic shielding. Okay, so basically this will be a key concern. Okay, so if your noise source is actually low frequency magnetic field, then you are going to have a bigger problem, okay, to solve this. Okay, so basically these two are the same. As I mentioned that for far field, they actually classify under this plane wave. So they are actually the same. As for the plane wave, okay, basically they don't exist in the low frequency, okay, because as I explained earlier on, at low frequency, okay, you're going to have a high so-called wavelength, and therefore we don't have so-called the near field under the plane wave. Okay, so basically plane wave actually happen at high frequency, so therefore you can imagine that they have much more easier to shoot. And most of the time, because of high frequency, the absorption loss will be the dominant factor. Okay, so the concept of separate E and H field. Okay, so basically in short, okay, for plane wave, the E and H field, they actually converge. So therefore, in this simple conclusion, if the noise source is E field, okay, the problem will be easily solved. Okay, be it the low frequency or high frequency, we will be able to curb this problem easily. However, the challenge will be on the magnetic field, especially at low frequency. Okay, you can imagine that even for reflection or absorption, is not going to be effective. However, if the frequency is higher, you probably can have some form of curbing of magnetic field, because for high frequency, it is mainly dominated by absorption loss. As for brainwave, I don't see any issue. Okay, we can easily shield against brainwave. With this, I'd like to end my discussion. Please help to like this video and subscribe to this channel. Once again, thank you so much for strong support. I hope to see you guys. Bye for now. Thank you so much.